Yeah. Okay. So yeah. Okay. Fine. This is your penultimate week for your NPTEL course on advanced quantum mechanics with applications. Uh, so now one more week is there, which like you would be wrapping up things quickly, and then I hope you are moving better for your tests. And as we know, like last time we were continuing our discussions about perturbation theory, so we'll keep on that. And also, like there are a lot of lectures already been uploaded on your NPTEL portal, including the final week's lectures and assignments. So hope you like going through well, and any problem you can report it right here in this problem solving session, or even uh, like other means, like I mean you can reach out like discussion forum. So hopefully someone will try to reach there. So yeah, last time around, like we introduced the idea of like perturbation theory, and like how we deal with a degenerate perturbation theory or a non-degenerate perturbation theory. And so moving on those line, we have another version of this perturbation theory. This again comes under the approximate methods, which we will see as variational principle. So, uh, like, what is variational principle? Like this is for some. I mean, a variational principle basically gives you idea that, like, for any given generic behavior potential, so you can like you can estimate what is the ground state, or you can at least estimate what is the uh, bound, the minimum, the bound at most which your ground state can be, uh, is given from this variational principle. So so no, so to understand, like we have some, we will take some any normalized trial wave function. So that is like we are giving by as psi. So in this state, that your Hamiltonian, if you take the expectation uh, uh, value of your Hamiltonian, you'll get some energy, and that uh, will be always greater than your ground state, or or if that state itself resembles some ground state configuration, then that has to be equal to your ground state energy. So this is something which we can also understand from earlier intuition of understanding what are ground states and excited states. So that's what this variation principle is also talking about, like more or less like uh, the same idea, like, is depicting in this principle, which we have seen through various intuitions over different study of quantum systems so far we have dealt with. So yeah, uh, it gives the upper bound for the ground state for any normalized sign. So, uh, like for example, like we can see like uh, like we can see quickly how this variation principle works through this example right here. So um, find the best bound on ground state energy for the one-dimensional harmonic oscillator using a trial wave function of the form this. So, so we are given any arbitrary state. So this is something like, for example, we know like a one-dimensional harmonic oscillator like doesn't necessarily has to be in this wave function. So we have seen like earlier, like in previous quantum mechanics courses, and also in previous like I mean topics that I mean I'm talking about the harmonic oscillator, where I mean where exactly we started. So we started with some uh, potential, which we know quadratic potential. The behavior is quadratic in nature. So from that potential, we try to solve Schrodinger equation, and from Schrodinger equation, we found solutions which are basically which reflected the wave functions of harmonic oscillator corresponding to different energy levels, so corresponding to different excited energy states or ground state. So we have seen like if you remember, like we used to have something like the wave function would go something like uh, I mean alpha square a square, some Gaussian type nature, and some you also had some Hermite type polynomial, and with some normalizing constant, all this. So that is the generic. I mean the actual eigenstates or eigenfunctions which you get when you solve for a quadratic potential with something like goes as half m omega square x square. So for this kind of potential, like you added with this kind of eigenfunctions, which we thoroughly seen by solving Schrodinger equations explicitly with precise conditions, with precise ground conditions, and so on. So, but in general, like your harmonic oscillator can have some other form of wave function, like which is given right here, because the wave function which we were earlier talking about, the eigenfunctions of harmonic oscillator, which are Gaussian in nature, or Gaussian also includes the Hermite polynomial. So that is very specific for a region that we were solving for a very ideal system. But now, if your system is not idle, that is what generally we see practically. That is what how every quantum system exists. So in those cases, like some other arbitrary state can be, your quantum system can be in some other arbitrary state, which is nothing to, which won't be exactly the same as your ordinary eigenfunctions when you solve for ideal harmonic oscillator. So this is again like the psi of x. It can represent your eigenstate or some wave function of your harmonic oscillator, uh, which you not necessarily try to relate it with your, with your eigenfunctions of a one-dimensional harmonic oscillator, which generally comes in the form of this nature. So, because now we are dealing with some non-ideal harmonic oscillator systems whose wave function can be typically of some other form, uh, which is uh, which is not exactly has to relate with this nature. So yeah, so that is what like it is given. So if your harmonic oscillator do exist in some sort of this state, which is a over x squared plus b squared, this is something sort of a uh, I mean uh, Lorentzian type wave function. So in this case, like what could be your ground state, or like what is the bound to your ground state? Ground state energy is what you have been asked here to estimate, and that we will do using the idea of uh, variational principle. So yeah, so then what you got to do here. So first uh, first thing you have to first like uh, estimate what is a is your normalization factor. So so first thing is to calculate what is a, and once you fix a, then you can move on for rest of the calculation, or you can also do at the end also, because that won't affect uh, your calculation as such. No, I think you have to do it from the first, because the ground state indeed would depend on this factor. So yeah, you even if you keep it in terms of a, like at the end you can find it, but let's like calculate it right from here. So yeah, so your normalizer is uh, psi star psi dx is 1. So then you take a square and 1 over x square plus b square square integral dx equals to 1. So uh, this integral goes throughout the space minus infinity to infinity. So then you have to find, so you can apply the identity of, the even functions to solve this integral to make this integral to simplify this integral. So your integral limits now becoming 0 to infinity with an additional overall factor of 2. And so yeah, so like if you would solve this, like you can do some substitution over here, and its integral result, its value would be uh, is 2a square pi over 4b cube. That is 1. So this will give you your a would be 2b cube over pi. So that is just your normalizing constant. So once you have the normalization, so you have your normalized state, that is 2b cube 1 over x squared plus b squared. So now you have your uh, quantum harmonic oscillator in this state, and so now in order to find the like minimum bound, so first you have to calculate. So you need uh, this quantity. So basically, this means you need to calculate the kinetic energy term plus the potential energy. So for kinetic energy, you can do, like, kinetic energy is your E square over 2m. So when you write it in terms of operators, that becomes minus s power square 2m. Uh, then del square then x square. Uh, so we are taking expectation energy. So that means, yeah. So first you will have the same wave function. So this will be 2b2 by your, so that square root will become square. I mean, you square it, it will just become 2b cube over pi, the overall factor, and you have this thing. So that is the constant part, and this now the your kinetic energy is to operate on this. So that is dx. So again, it differs from minus infinity to infinity. So then, uh, first you have to solve this. action of this differential operator del square or del x square over 1 over x square plus b square. So that will so that will become following. Uh, so let me uh, write it over here. So 1 over x square plus b square. So when you take first derivative, it will just be minus 2x uh, x square plus b square whole square. Then yeah. So when you take it again, so your next derivative like would become so you do the derivative one more time. So that would give you following x square plus b square cube. Right. Yeah. So now then your expectation energy would become uh, yeah, okay, 0 to infinity 3x squared minus b squared x squared plus b squared 4 dx. So yeah, then uh, so then you have to solve this integral. So and you can again uh, like try to solve this uh, maybe uh, yeah, using or you can just separate this out and individually you can try to solve them. So this would be uh, so this is fourth power uh, yeah, 0 to infinity x squared squared okay 2x squared okay. So yeah, this can be now you can write this way 1 over x squared plus b squared cube dx then minus 4 b square 0 to infinity 1 over x square plus b square 4 power dx. Yeah. Uh, yeah, fine. So yeah, then now you can have this integral. So which will give you pi m 3 over 3 pi over 16 b square. So upon solving this integral, you get this result 32b7. So yeah, so that is h bar square over 4 and b square. So that will give you the uh, kinetic energy. And so now when you have the kinetic energy, so now next you require to calculate what is this potential energy, and that will be So the potential energy would be simply half m omega square psi x square psi. So that is you are able to calculate. So you can calculate what is square. Uh, so like x square, like you can write x square 2 times 0 to infinity x square plus b square, and then this is square dx. And yeah, and yeah, then that is, okay. So yeah, so when you try to solve this integral, so again you can see you can do a substitution, and using the substitution you can calculate this integral. So so that means like this will give you uh, so for this link you will have uh, so so like this integral you can check this out, like this will give you pi over 4b. So yeah, and also yeah, I forgot the normalizing factor. So normalizing factor, you have this 2b cube over pi, uh, that is square root. So this will ultimately become 2b cube over pi. So times 2b cube over pi. So your finally your expectation energy for potential energy, like would then become uh, half m omega square b square. So this is just in normal, like I mean the differentiation and integration, like largely it involves like nothing more like conceptual thing you require here in between these steps. Like this is straightforward calculate differentiation and integrations, and so ultimately you will arrive with your expectation value of Hamiltonian. So that is basically, so your now expectation of Hamilton is now um, x bar square for mp x bar square for mp square plus half uh, m omega square b square. So yeah, now so the statement which variation principle says like we want the like the uh, minimum bound on the uh, I mean, minimum bound on the expectation value, so that uh, it has to equal to the ground state. So for the ground state energy, you need to ensure that this expectation like shows the uh, minimum bound which your I mean your expectation value can be equal to the uh, ground state energy. So since for the uh, minimum bound, and like further like in this question it is also said that there exists a parameter in this wave function that is b. So controlling this parameter b, so which is said in the question that it is an adjustable parameter. So controlling this parameter b, you can make your wave function to attain the state of a ground state configuration, so that when it when you control the speed specifically, when you tune this parameter p to a particular like value, so your finally your the state which is given right here, the trial wave function, will ultimately attain a ground state configuration for your given harmonic oscillator system, and that will correspond to the ground state energy. You take the expectation of Hamiltonian in that ground state. So, like what is, so how can we know like what is the particular value of p, so that like your uh, the given wave function would behave uh, similarly to corresponding to the ground state. So for that, like like we have this expectation value. So for the uh, we have expectation value in terms of p square, that in terms of p, so we have to choose a particular value of p so that it corresponds to a ground state energy. So we need to calculate the extremum case where p attains a value such that it would correspond to a ground state energy. So to achieve that, so we first have to know what is p, what is the value of p, which corresponds to ground state energy, so that we can know by the first derivative of this expectation value of h with respect to p, going uh, making it to go zero. So that is the way we check the extremum conditions. So just you have to take with derivative with respect to b, and that would basically like give you uh, minus h bar square 2, and this will give you 2 eq. So yeah, then again with respect to b, that becomes omega square b going to 0. So yeah, so when you try to solve this, like this, like ultimately becomes b4 h bar square over 2m omega square m square omega square. So your b square is h bar square root 2m omega. So yeah, so now your b square is this. So that means you can have your h uh, minimum, that is uh, you just have to substitute this value of b square. So your b square is this, then this was going 4m. So root 2 omega or h bar is your 1 over b square plus half omega square h bar over root 2m omega. So like you solve them, like you you will get this like something around 1 over root 2 h bar omega. So yeah, and you will see that like this value is so otherwise this can be written as 2 h bar omega. So you can see this minimum energy is greater than uh, root 2 h bar omega is greater than half h bar omega, uh, and this is for ideal harmonic oscillator uh, ground state energy, ground state energy. So yeah, your minimum energy now, like uh, yeah, uh, like this has for corresponding to the given wave function. If you have such kind of wave function, the minimum energy bound like it will have corresponding to the ground state will be root 2 times your uh, ideal ground state energy. So if you denote your ideal ground state energy as E naught, that is half S for omega. So now your E naught prime will become root 2 E naught. So that is like how, I mean, variational principle gives you I mean, an estimation of your ground state energy bound corresponding to the given arbitrary wave function for which your system ideally do not uh, have that configuration, because the wave function which we started, it is not the ideal eigenfunction or yeah, for your given harmonic oscillator. So that is what you would have like if this would be this kind of wave function, which is something of Lorentzian type behavior. So yeah, so like, is this like clear for you or any problem?
Hello.
Yeah.
Okay, so the idea is that if you have an ideal function,
uh,
then ideal eigenstate, then the energy is half a state omega.
yeah, yeah,
Okay.
right.
But if we have any arbitrary wave function that is not ideal to the harmonic oscillator,
Right.
then you can follow the path of variation principle, and from
Mm.
that can get a limit
Yeah, yeah, yeah.
of the ground state
Ground
energies
state.
with respect to the ground state energies.
Yeah, and that limit,
So
like, how would you get? Like, you will get by controlling a parameter which exists in your wave function configuration. So in this case, it was B. So you control it in such a way that it will always like give you the minimum bound. And how do you understand that? Like, you understand it when you make it when you take the first derivative of expectation value of H going to 0, because that will fix the value of b, that will fix the value of your parameter b, and so if you, and when you calculate what is b from this condition, you will attain your wave function in your ground state configuration for the non-ideal case.
so I
Yeah.
can take any form of the wave function. Yeah.
Yeah, you can have, like, that depends on your system. So this time, like, we are not bothering about like what wave function it could be, because last time around, or you may have know this before, like, we were like, while we were doing perturbation theories, like, we see like how to incorporate corrections like into your uh, uh, given ideal wave function. Like, for example, like last week we tried to solve for this delta function potential or something, some different perturbation, different sorts of perturbation we have seen. So for each given type of perturbation, we were solving what would be the change in wave function. So the change in wave function was something like, we have the original wave function, unperturbed wave function psi 0, plus some epsilon times psi 1, like something, some correction we were incorporating into it. But now we are not bothering about any wave function right here. We are just simply calling it. It can be any arbitrary form of wave function, well-behaved wave function, like well-behaved in the sense, like, which we know, like, wave function should obey the
It should
other.
be normalized,
Yeah,
normalizable.
right. Yeah, continuous and all other, yeah, properties which you know very well. So, so if that wave function would be given, because your harmonic oscillator can remain in any situation, which you can only probe it after understanding what are everything influencing that system. It can be environmental effects, it can be some other measurement effects, some, yeah, any effect can be influencing your harmonic oscillator system. So, yeah.
Okay.
So, okay. Anything else? Like, did you get it? Get my point?
Yes, yes, yes.
Okay.
But we
Yeah.
can only give a bound for the ground state, not for the higher energy state. fast
uh,
state, fast
yeah,
accelerated states.
yeah. First
Say,
excited state also you can try to uh, get it from here, like first excited state. Because ground state we know, because we have this condition which what we are doing, uh, because we know like it has to be minimum, so we take the first derivative with respect to b and set it to 0. But first excited state, you can like what you can do after knowing the ground state, like you can tune your parameter b. So like you will change your parameter a little bit, what happens like when you change your parameter b from this value h bar over square root to m omega, any other value, it will give you the excited state energy, excited state configuration, because this is the only value which corresponds to your minimum state. But if you tune this value to some other, if you change it even minutely, like you will get the subsequent excited states configuration. But you have to be sure like which excited state it has to be, and that cannot be like as straightforward what we have done this way. You know the minimum bound, so you tune this b value a little bit so that it will give you the subsequent excited states. Like,
okay.
so you know this is the value. Start from this value, slightly tweak this value a little bit more. You will get a expectation value which would be greater than your ground state energy, and then you will
Suppose,
again tweak. You will again get another expectation which will be greater than.
suppose
Yeah, yeah.
you have given a state
Hmm.
wave function
Hmm.
for the first excited state.
Huh.
Then you can follow the same procedure because in the first state from that state you have to find out the b, following the same procedure.
Yeah, yeah. You are telling sorry, I didn't get what was your question?
I'm saying that here you are given the ground state wave function.
Hmm.
Suppose you are given given the first state wave function, the form of the first state wave function.
For
Then
yeah.
you can
Uh,
then you can follow the same loop.
uh, yeah, yeah. Like you have to again choose a particular value of b. So that would again I mean again will set your first excited state energy. I mean, because
Yes,
how
yes.
we did we again uh, I mean we have to fix a particular value of b so that it would correspond to your minimum bound energy.
Okay. So you're saying that B is a conflict parameter. So from the equation, it is saying that it is inverse to the frequency. So it is related to something frequency. Yes,
Yeah, it can
this
be.
B.
It is it is inverse of h bar square root to I mean h bar over square root to m omega. It can be it need not be this parameter has to be of this form. It can be of some other form. It can be sometimes it can directly depend on frequency as well. So there is nothing any hard and fast rule
But
as
it
this
is a
work.
tuning. It
Yeah,
is
it is a
something like tuning.
tuning. Yeah.
Okay. Thank you.
Okay. So, uh, like anything more, or
No, it's
okay.
okay.
So, yeah, another example we can see right here. So, we have to find the lowest bound on the ground state of hydrogen atom using the Gaussian trial wave function. Uh, that is psi of r, which is a e exponential of minus b r squared, where again your a is your normalizing factor and the b given here is your adjustable parameter. So again you have to repeat the same exercise what we did before to in order to estimate the ground state bound for the hydrogen atom. So again, this is not your ideal ground state form which you would normally see for a. uh, I mean hydrogen atom. So then uh, so again, yeah, like we'll start from like what estimating what is normalizing factor. So that is we like again psi star psi. Uh, so dV is your volume because now you have a three-dimensional system. So that has to be one. Then that means uh, you have uh, a square, then exponential minus 2b square, 2b r square. Then you have your volume integral uh, like measure, that is r square sine theta dr d theta d phi. So yeah, then that has to be one. So uh, so this time you have a like a spherical symmetric hydrogen atom system. So you know very well that like for hydrogen atom system, so your three-dimensional configuration, uh, like I mean, you have a spherically symmetric potential for which your wave function you see here the given wave function is also not dependent on any sign or theta or phi terms, so you can separately integrate out by factoring out alongside your R integral. So for R integral, I'm writing your limit will go from 0 to infinity. So 0 is where your nucleus of your hydrogen atom is residing, and you integrate it till infinity. That is r square dr, and alongside you have this sine theta d phi. So, and for this, theta will go from 0 to pi, and phi will go from 0 to pi. So, again, I hope you all are familiar with this. So, this will become 4 pi a square. And this integral, I think you can calculate it from your uh, gamma integral identity. So, so gamma integral identity will give you then 4 pi a square. Uh, so, so this will be okay. So this will give you pi over 2b, 3 over 2 equals to 1. So I hope like you are familiar with gamma integral identity, right?
Hello?
You're familiar with
Yes.
gamma identity integral.
Yes, yes, yes,
Okay.
yes, yes.
So this will be your a normalization vector is 2b on pi 3 over 4. Okay. So that is your normalization factor. So now you have your normalization factor again. Then uh, you got the ground state configuration. Uh, so in this ground state configuration, you have to find the like, minimum bound. So so again to see that we have to again first have to calculate this expectation energy. That is uh, so then your kinetic energy expectation will then become again similarly minus s bar square over 2m. Uh, then this time you have to uh, So yeah, minus h square 2 then you have this normalization factor right here by 3 over 2, then integral minus b square r dr square, dr square, then it will, then your derivative operator minus b r square, r yeah, then you have r square sine theta dr d theta d phi. So now, like for this is basically your so in three dimensional, like, or in spherical coordinates, like you write your differential operator, your del square, something uh, 1 over r square, del over del r, then r square r del del r. So using that, like, you can calculate what is your uh, del square exponential minus b r square. So like you just have to take this, I mean, series of derivatives right here. So uh, which will give you minus 2b over r squared, 3 r squared minus 2b r 4 minus b r squared. So yeah. So after then you have to calculate. Yeah, you can use this and your expectation for your kinetic energy that will then become. So yeah. So basically, in the integral, we have 3r square minus 2b r fourth, r fourth exponential minus 2b r square, 2b r square, that is integral with respect to dr, 0 to infinity, and also is there some other factor? Let's see. Yeah, so this minus 2b factor is there, and then from your angular part, from your sine theta, from your d theta d phi, you have a factor of 4 pi, so which comes from your integral over d theta d phi. So yeah, then that basically becomes your final. Again, you will see here uh, this integral you can again calculate it using your gamma integral identity. So that is so from there you can find this first the first term will give you 3 over 8b, and then 3 over 16b, that is equals to 3 h bar square b over 2. So yeah, so you got your like kinetic energy Expectation, similarly, you then have to find out what is potential energy expectation. That is, uh, again, you can write your potential energy for uh, your potential energy for your uh, hydrogen atom is given by this 1 over r potential. So, to be by, so basically taking uh, this, I'm basically taking this, so 1 over r, uh, basically give you, uh, so you have your normalization, that is 3 over 2, integral uh, is 2 r square, 1 by r square dr, that times 4 pi factor, again. So this again goes from 0 to infinity. So yeah, so again, you again will have to use this gamma integral for this integration right here, and like you will find out your potential energy for V will basically uh, give you minus E square of 4 by epsilon uh, 2 times of 2B pi. Yeah. So again, you have your potential energy right here. Then uh, then you have your expectation energy for total Hamiltonian, which is uh, 3 h per square B over 2m minus uh, minus E square 4 pi epsilon naught B 2B over pi. So again, uh, to get the minimum bound configuration, we have to take the derivative with respect to b, so that you can control b in such a way you can get the minimum bound by setting it to 0. That is, so that is 3h bar square 2m minus 2 square 4 pi epsilon naught. Uh, that is 1 over root 2. So, that is root 2 by 1 uh, minus half equals to 0. So this will give you uh, e square 4 pi epsilon naught square uh, 2 yeah 2 by pi square root 2m over h bar square. Okay, yeah, that is 3h bar square. So this is your b. So uh, at this b, like you will have your bound. So substituting this p for your expectation energy will give you the minimum energy bound. That is, so if you just substitute it, like you will find that will give you minus m over h bar square e square 4 pi epsilon square root over 3. So again, like you will see from your ideal hydrogen atom system, this is this much difference. I mean, it is a different by 8 over 3 pi factor. So your E1 is uh, minus 13.6 eV for the for an ideal hydrogen atom. But now, like if you would solve this, like this will give you a value around uh, minus 11.5 eV. So this is greater than your uh, your I mean uh, the ideal case value of minus 13.6. So this is again, you can see like how having a different ground state can change your minimum bound energy quite significant. So that was this question was about on the hydrogen atom, similar to the one which we like solved for your the harmonic oscillator. So is this clear for
Yes, yes, absolutely. The procedure is the same.
sorry?
The procedure is the same.
Yeah, same. Just now it is hydrogen atom. So now hydrogen atom, like you can see your ground state now uh, have has this energy minus 11.5 electron volt. But ordinary, which you see for an ideal hydrogen atom system, you have minus 13.6 electron atom for the ideal hydrogen atom.
So any arbitrary wave function gives you higher bound for energy.
Like because I mean your that is what like ideal case can give you the minimum bound, like your wave function is so I mean unperturbed, like it is it is not it is not capturing any other influence, like like for example when you see ground state, like it does have your measurement effects, your environment effects and all these things. But in general, like the ground state which we solved it from Schrodinger equation, that is for very regular closed system, which ideally we don't see it.
So here nothing about perturbation. Just we have considered an arbitrary wave function and
Ah,
you do the
yeah,
minimization
yeah,
handling parameter, then you can get the energy,
yeah, yeah,
uncertain value of the energy.
yeah.
So nothing to do with the perturbation.
Perturbation. Like because we are not like adding anything into the Hamilton, like because why we do perturbation to know what is the actual what is the change in the form of wave function and energy. But now as we know, since we know directly the wave function can be some of some arbitrary form through some experiments and some other process, we got to know that like it can be of this state, then we can generalize that state for different. I mean, we can set a bound for that given corresponding state, like it would have this minimum energy corresponding to its ground state. So because we have the wave function in hand, so we are not calculating anything. We are not like following the prescription of perturbation theory to know what is the state and what is the change in energy, what is the change in state. So that is what we are not doing here.
Okay.
So,
Okay.
so
Thank
hope it is clear.
you. Okay.
Okay. So next, like there's one more question related to it. So, We checked if there was one person reading criteria. Which, okay, there was a one person similar to it, like, but it had some important results for that, but I was not getting. But anyways, I think it was something related with the first excited state. Like, I mean, you were asking about the like what would happen, like similarly if we can know a first excited state or something. Like, you were asking one such question, right? Like, what I remember, like I'm not getting that question right now, but for the first excited state, like what you can do is like if you are given a trial wave function and that is orthogonal to the wave function which is given right here. So similarly, you can set a bound for your first excited state energy. In that case, like what would happen? So uh, the I mean, in that case, like uh, your variation principle now, like would say that like psi psi is greater than your first excited state. Uh, Let me call this a psi prime. So where this psi is orthogonal to your ground state. So this is your ground state, and this is some excited state. So like upon controlling the value of psi prime, it would depend on some parameter, again some parameter like b, and you can control that parameter such that like it will set uh, this lower bound for this first excited state. So so that is the other way you can say variation principle. Like, I think that is what your last question was similar to, like, uh, hello Mehdi. Hello.
Hello.
Yeah,
Yes, yes.
did you get like what I was telling right here?
Yes, if the ground state is orthogonal to the.
Yeah, I mean,
Yes,
if
yes.
you have like if you want to know, you want to check the other way around, like what would be the bound for the excited state, for the first excited state, you first have to ensure the wave function which you are like having the trial wave function. Like for example, the trial wave function which we had is this. You will have another trial wave function for the first excited state, which would
Okay.
be orthogonal to this ground state.
Okay.
And again that is also dependent on some parameter b, and if that is so, then again you can take this I mean, for the uh, bound case, like for the lower bound case, you again have to take the derivative of this condition which I was dealing with that time. Again you have to check this, you will get a value of b, and when you put that corresponding to that uh, wave function which is orthogonal to ground state, then that will give you the minimum bound, or the the bound for your first excited state energy corresponding to that value of b. So
Yes,
hope like that is what you were trying to say that time.
yes, that was my question.
Okay,
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 thank
yeah.
you.
So uh, yeah. So again, like this time, you have this here. So I think I can just tell it just over the point. I mean, because this is again similar to what we have been doing so far here. So like I can just quickly tell you this is something which I have given because you see this kind of potential very commonly. I mean, see around most of the time. This is you cover potential, so you get this this kind of exponential term. So, like in nuclear system, you will see this is a very important potential. So, uh, here also it is said like if the photon had a non-zero mass, then the Coulomb potential would be replaced by this Euclid potential. So this kind of situation you will see in nuclear potential. Uh, so where your mu becomes your m gamma c or h bar. So using the trial wave function, estimate the uh, binding uh, energy of hydrogen atom with this potential. So. Uh, so for this if you have this kind of potential, and suppose if you are taking your trial wave same as your uh, the ground state of your hydrogen atom, so your ground state of hydrogen atom would be something with the normalization is this uh, minus r over b. So then you will find it the okay. So in the same way, like you can calculate what is expectation of kinetic energy. So that will give you something. Um, so that is h bar square over 2 mv square, and same for potential energy, which will again give you e square for pi epsilon naught 1 over b 1 plus mu b over 2 square. So using this, like you have your what is your expectation for your ground state or expectation for hydrogen atom. Then again you will do the same thing. Like you take to 0, and this will give you a specific value of b. Uh, so in this case you will have b. So this will be a bit long calculation you have to go through. So b can be given as 1 plus 3 mu b over 2 over 1 plus mu b over 2 q equals to a. So where a is your core radius. So a is your core radius. So now like we can write this uh, core radius, like you will see. Like since this is you use the exploit this condition of mu a is very much less than 1. Uh, mu a is way less than 1. So in this equation right here, so then that will give you uh, b 1 plus 3 mu b over 2, that is the numerator part of uh, this equation. So in denominator I am using this binomial expansion, minus 3 mu b 2 plus 6 mu b over 2 square, so up to second order, then that will give you b 1 minus 9 over 4 mu b square plus 6 6 by 4 mu b square up to second order, and there will be more such terms. Yeah, there will be, which are we are skipping right here. So we'll see 1 minus 3 by 4 uh, will be square. So this will finally give you the value of b, which is equal to 1 plus 3 by 4 uh, mu a square. So like you can think of like your b, your parameter b is basically your bore radius with some additional correction. So if you have this kind of Yukawa potential, instead of a spherical symmetric, instead of the 1 over r potential which you earlier had for ideal hydrogen atom system. So for this kind of potential, you will see your like your effective bore radius is something like goes like a plus with some correction, and uh, this parameter b is basically your effective bore radius. That is your, you can say, your new bore radius for this thing. So now like uh, so then like what you can write here. Uh, so basically, like what I did here, there is one more approximation like involved right here with this step, like because you'll see that your b is basically a over 1 minus 3 by 4 mu b square. Since your B is your second order, like which is already like a very small quantity, and like we know that mu a is very much less than 1. So like you can replace this mu b, like I'm like when I'm taking the binomial expansion for the denominator case, I'm replacing b with a. So because both of them are, like your b is already in second order correction, so you can effectively say that like your bore radius is something a plus uh, some correction. So then you will calculate your h minimum with this value of b. You will get something e1 1 minus 2 u u square. So again, E1 is your idle hydrogen atom system ground state value. So this was like to make you understand like what is this uh, parameter B actually like involves around, like how it can be like this is something, this parameter, like when you are changing the effective like value of the effective radius, which by technical it means like your parameter b, and that parameter b is like how inherently is linked to your system's property. Like this is what something you are trying to say, like how it is depending inversely to the frequency. Does it depend on that? So it can be any parameter which can significantly control the dynamics of your quantum system. So, so in this case, like you see, like it is something relating with the effective core radius, like which when you compare it ideally, you have core radius something a, but now you have some correction due to the potential which we have considered here is exponential minus mu. So is this clear for?
Yes, yes.
Okay. Any problem or?
But this problem,
Yeah.
the hydrogen atom, say, can you tell me where I can get the explanation or this kind of problems of this, especially for this problem?
Uh,
Third one.
Third one. Yeah, like
Yeah.
I mean, you can.
This one. Because as you say, in the question is written that if the photon is massless, so that's why which book or
I
where I
mean,
can get
like
this
the
kind.
photon is massless. Like I mean, like it need not to be like there are some other, like photon is generally a force carrying particle. So like I mean, there are other like you will see like in nuclear potential, like the strong interactions, you will have those force carrier like particles like having they would be
Mass.
messy. So yeah, they would be having some mass. Like in those kind of system, like you get some kind of this potential, but we are not talking explicitly in any nuclear physics context. So that's why like we are
Okay.
telling this as some, let's say, assume that it has some mass. But like in general, like this you will see in case of nuclear potential where it involves strong interactions where force carrier would have some kind of this factor mu, that is m gamma, which is the mass of that force carrier particle times c over h bar, and that is how you get this potential.
Okay.
So, but in general, like you will get in nuclear physics, you can check it. So yeah, so then that was about your variation principle. So now we can talk a little bit about WKB method. So so again, like if we would discuss WKB, like I mean, I would suggest like to understand this better, like you go through the lecture videos which is already uploaded. So it's due to very short time, like we can go like what the basic idea is about the WKB method, and we will try to see like some example how we can like uh, try to analyze system treating this WKB method. So um, so WKB method is basically like a is like a semi-classical approach. Uh, uh, say semi-classical approach. Uh, it's a semi-classical approach to solve your, your Schrodinger equations involving some potential which is slowly varying. Slowly varying in the sense, for example, if I have something, uh, let's say for some potential, if I have some constant potential, like if v of x is something constant, k something v naught. So we know like potential barrier system. We must have seen this kind of potential already well before, like the infinite potential itself, like which is zero for some range in uh, like from like for some range in the one dimensional space, or if you're considering the total. So but we are this method is like explicitly will deal with one dimensional systems. So let's say for the barrier system as well. So we had some potential which is constant. For those kind of potentials, like so like our like solutions generally had this form, where k is again some constant that depends on this potential. So k is the wave number associated with the wave function of the particle. So, but now, like if suppose if the potential is something slowly varying, uh, like for example, I mean, it has some turning point. Let's say this is A, this is B, this is X. Like for now, if you have some potential which is slowly varying, which is no more constant, then for those cases, like you have your wave function, something like behaving, uh, your wave function can be approximate to this uh, exponential I sigma x h bar. So now you see your wave number, which earlier used to be some constant, which directly depend on the potential. Now that is also changing uh, because you have sigma x. That is like I mean the wave number something you were denoting it as something 2 e minus v naught over h bar, like for this case. But now like since your v is changing, v is slowly changing, so now your k will also change that's why like your k will be dependent on x. So now you can approximate this kind of wave function. If your wave function is slowly varying, uh, then uh, yeah, then if you use this solution like in your Schrodinger equation, so you will have uh, this condition. So from Schrodinger equation, Schrodinger equation, you get minus IH del square sigma del x square plus del sigma del x square equals to b square. Yeah. So from here you will see that uh, like you can like one more thing what we can do, we can write this sigma in terms of a power series. So for leading order, like uh, for leading order, if we consider sigma to be uh, like since we are doing a like classical approach, so we can always expand this as some kind of power series in h bar. So like up to leading order, you will see sigma naught. I can write this as del square sigma naught, or not del square, that will be zero. So del, del x, yeah, equals to p square. So so in this case, like I can, what I can write, that sigma naught can be, this. So in this way, like I get what is sigma naught. So then for the uh, but that is not the total uh, form of sigma, because I have other leading or other corrections or other terms which is contributing to the overall sigma x. So which like what we can do uh, for the for all other case, like we can say del sigma by del x is to e of x, and e of x is equals to 2 pi h bar lambda x. So that is the like momentum which we write in terms of the wavelength. Basically the your de Broglie wavelength. So uh, so for the like we were uh, so now let's say if sigma, if we return sigma to its first order in h bar, then your Schrodinger equation will read minus I square del square del x square sigma naught plus 2 del x sigma naught del h bar right, then del sigma 1 over del x equals to 0. So uh, so using this condition, like I mean there is there is one more condition to it. Uh, the h bar square del square sigma x is lx sigma is less than 1. So so what I'm doing here, trying to, like, as I estimated what is sigma naught, like I'm trying to uh, like approximate what could be your sigma 1. So your sigma 1 like will generally now dx you will see that del sigma 1 is basically del xp over 2p, that is sigma 1x del dx. So exponential of sigma 1x will give you 1 over root dx. So like what I'm trying to say, like when you have when you have slow varying potential, so I have a uh, I mean I have a wave number which earlier it was constant, now it will be some function of x. So uh, that is sigma of x, and that from Schrodinger equation that will go like this something. But for this kind of differential equation, like since we are working in classical limit, like since this is a semi-classical approach, we can like expand the sigma in terms of this h bar, like in terms of this h bar orders. That's this way, where the first order, like, I mean, we can we can take the first order, leading order sigma naught, which can be stored as like that is uh, basically equal to plus or minus the momentum p of x d's integral, where p of x is basically given as del sigma by del x, or that is basically 2 pi h bar over lambda x. And for sigma 1, like, you have to again like use this sigma, that is sigma naught and sigma 1, including sigma 1, and from there you will find a sigma 1 relation that is given like this, or which is basically this. So I mean, like, what why I'm doing this, like, I mean, since, like, if I do this, like, I can write my wave function something else, uh, like c1 would be x. uh, uh, I mean, like, generally, like, we when our potential was constant, we just simply used to write like some constant a I k x plus b minus I k x. But now, instead of k, we have sigma, which again has two, like like sigma. Now, like, if v naught goes to something v of x, then k goes to sigma of x, which is sigma naught plus uh, h bar I sigma 1, like up to first order in h bar we are considering. Then in that case, uh, what happens, like, your solution will then become some constant a, uh, exponential, uh, uh, yeah, some constant a exponential, uh, I sigma of x, x plus b I sigma of x, x. So that will basically become c1 or root bx exponential I over h bar p dx plus c2, again p of x, then minus I h bar p dx. So I am just substituting the form which I got right here for sigma 1 and for sigma naught. This is sigma. So I'm using sigma naught, I'm using sigma of x up to first order in h bar. So that will become my effective wave function. So, are you getting, like,
Hello.
yeah?
Yes, yes. So
Uh,
can you tell me that any example of this WKP acceleration?
okay, so yeah, that is what I'm trying to go through. So, in this, like, I mean, the explanation which I'm giving right here, you can get a more explicit, detailed explanation if you check out the videos, because there will be a lot of steps which I'm skipping right here, like lot of arguments and steps, because I'm just trying to say, like, how under
But the
WK.
main thing is that if you have a potential like that,
Your wave
simple
function.
potential, then
uh,
you have the planar like wave function. But if
uh,
you have a slowly varying potential, then your wave function will be modified
yeah,
based on the wave number
yeah, based on the wave. And wave number, we expanded some order of
process.
h bar into a series, in a series, that from that we get this effective wave function.
Okay.
So yeah, and also, uh, like, yeah, that is one part of it, like how the wave function would change. And also furthermore, like there is something you need to know, like the boundary condition, or not the boundary, I mean the turning points. At the turning point of this wave function, again you will see that like your momentum would be changing, your momentum would be going zero. So in that case, you again put another condition from there, which you get basically you get another condition for PDX is 2 pi h bar n plus half uh, from turning points. And this is basically your uh, Bohr Sommerfeld quantization condition. Okay, so was there something else to talk about here? Uh, So, like if you again again like you can check like how this appears, like why from the turning points this will turn out. Like you will see that like at turning points, your like the solution to your Schrodinger equation will become something sort of airy function. So in this case, like which we were trying to discuss here. So like at turning points, like I can just briefly say turning points your like or will become something of the form p of x 1 over h called some p dx. Uh, but we know like at turning points, uh, like classically, since we are doing classical approach, we know that there would be like it cannot like go beyond the turning points. I mean, like for example, if we have a potential like this, and if some particle with some energy uh, E1, so the particle can go, like if it is perturbed from, let's say, from x equals to 0, then it can go maximum up to this point. So similarly, like if some uh, has some this energy that is equal to x equal to 0, like I mean I'm telling energy corresponding to this x equal to 0 line. So in that case, you will see that particle would go till point A, and then it will retrace back, and then again in the other end it can go till B, and it will retrace back. So it cannot like go beyond it. But in quantum mechanics, you see that like that is not the case. So so there will be uh, uh, the condition. You will see that like I mean you will see this. Uh, this will change to this thing. It will become something cos of pi by 4 minus 1 over h bar p dx. So Similarly, at the other turning point, you have two turning points. You will get another form is p of x cos of something 1 over h bar p dx minus pi by 4. So from this turning points, you will find that you basically get this condition, which is 1 over h bar p dx minus pi by 4 minus pi p dx equal to n pi. So let's say this is turning point around a. So this will go from x to a, and this will go from b to x. So b to x and x to a. So at n, this is equal to n pi. So n pi means like your, uh, I mean, yeah. So yeah. So n pi, like that gives you the periodic city. Uh, classically, this will happen. The classical notion is basically when it reaches the turning point at retrospect. So, uh, from this actually you get this condition that p dx, this line integral, you see that is our closed loop. So that means when you integrate p dx, I have p dx plus uh, x to a p dx. So that is like the complete from a to b, the whole potential when a particle moves, then that complete integral of this p dx will be this thing, 2 pi h bar n plus half. So that is basically a Bohr Sommerfeld quantization condition. So like this is just a briefly I'm trying to say like how this condition is achieved, but again, like we can see this in a detail like if you want to know. But quickly I can tell you an example as you were telling. So how this WKP can be seen. So for example, if we take again a harmonic oscillator system. So harmonic oscillator. So we know the Hamiltonian uh, is given as p square 2m plus half m omega square x square. So in this case, the momentum is basically 2m e minus m omega square x square. So uh, and yeah, so for uh, to calculate what is to calculate what is the form of a function, what we have to do here, uh, yeah, uh, we have to calculate what is integral of p dx. Uh, let's first calculate. For harmonic oscillator system, we know this is the momentum which it will have. Like the classical relation of momentum will follow this. So from here, what we can do. So this is basically like 2m e minus b. So the usual relation. But from here, from turning point, like from WKP, we have this condition. The line integral of p dx will give this thing. So now, if you do this, like what you will get, uh, uh, so line integral of this over closed loop p, pdx uh, will give you. So from uh, let's say minus x naught to x naught, these are the turning points. Dx 2m uh, e minus m omega square x square over 2. So if you integrate this, uh, before that you also need to know, because your x naught is a turning point. So to know what is your turning point, so you can say at turning point, you have energy half m omega square x naught square. So that is x naught is your, you have two turning points, that is 2 m omega square. So one is at minus 2e over m omega square and other at plus 2e m omega square. So we are integrating from those two uh, turning points. So uh, so like this is, since this is a line integral, I mean this is a line integral over a closed loop. So I'm going from minus x naught to plus x naught. Then again I have to go from plus x naught to minus x naught, and you will see that like the that contribution is basically that twice of that. And if you solve this, like you will get like if you try to solve this, like I can, like I'm directly writing the result here, just you have to do this integral. So that will give you 2 pi e over omega. And and surprisingly, like this will come out to be uh, 2 pi h bar and plus half. So where yeah, where this the yeah, where this e, this is basically en. So this e n is basically your n plus half h bar omega for harmonic oscillator. So this is basically like this line integral or p of dx. It is basically your xn for the given system. Like in classical dynamics, also I hope you know about this. Like this is your xn of the system, and from this WKB approximation, what it is saying, if you are having this quantum system, your xn is also quantized, just like energy. So so this is uh, the one of the ways to see like how this board sum-of-two quantization applies here. So and same way, like if you go on to estimate what is wave function, like I'm like directly writing it, like you can check this. So this will become c over root p of x cos n pi over 2 plus p over h per omega sin inverse x over x naught plus x over x naught 1 minus x whole square for 0 x2 x naught, and for x greater than x naught we have exponential minus e over h per omega again x over x naught. Um, so this is pretty big expression, cos hyperbolic inverse x over x naught. So this is the like the WKV approximation wave function look, and this quantization of PDX will look. Yeah. So the last part was bit quickly, like I have gone through like
Okay, okay, okay. I see the
uh,
books. So,
so like did you get the idea like what is happening here? Like we have a slow varying potential, then we have this kind of condition where PDX basically the this is another way to see like which we say like in classical theories we look uh, I mean we look the energy spectrum which is continuous, but in quantum system we have the discrete nature. So in this case, like you see this integral PDX, the xn is which we normally see in classical dynamics. Xn is one of the most important quantity, and that is also in quantum dynamics. You see from this Bohr Sommerfeld quantization condition, it is quantized over it when we integrate over closed loop. So, like for a harmonic oscillator, that would be equal to 2 pi h bar n plus half. And your wave function, like from this low varying potential, your wave function something would go like this. That is coming from here, which we you calculate what is PDX integral, and from there you get this. So this is like actually I mean this entire discussion would have taken like at least 2 hours or something. So like I just tried to sum it up in like 20-25 minutes. So that would be like I know something. A lot of things would have been skipped meanwhile while discussing a lot of things here. So but we can discuss even more detail if you want next time,
Okay.
or
I will
also
check
like
the
if
lecture first.
yeah, yeah, yeah. If you have any further any doubt or something like that, there's no problem.
So there will be 1 week, last week.
Yeah, one last week, and there will be one more also problem. So we will have like similar discussion like as we're having right now for two more sessions. I mean, one would be next week, and other I think after next week, the coming Wednesday, we will again have another session. So that time I was thinking maybe we can talk about something quantum information, like as you were suggesting, like to talk something more about quantum information topics, which was not
Yes. Yes.
uh, like you. I think you said it like you expected something more topics to be done, but like even last time around when we talked about we talked about few things and we ended up. So maybe we can talk about that if you
Okay.
are
Okay.
willing to help. And next week again we'll see. We'll try to continue this or some other topic on this water basin, and
Okay.
that's it.
Thank you.
Like and then we can have your. I mean, I hope like you are feeling this course better for you. I mean, this course is
Yes. Yes.
helpful to you in some way
Yes.
at least.
Because I know, because I have my background in engineering.
Okay, okay.
So in engineering, you know that we miss a lot of topic of quantum mechanics because it
Uh,
is related to physics.
right, right.
But if throughout this course now,
Hmm.
because you have two courses, quantum mechanics 1 and 2.
Okay, okay.
In general, in physics background students,
Okay, okay.
but as we are engineering, we
Uh,
didn't study this kind of things.
okay, okay.
So this course is designed in such a way that we can get some feelings of the topics,
Okay, okay.
advanced topics. So I think that it is a good way to learn
Okay,
within this
yeah.
short time.
Nice, nice, right. Right.
Yes, yes. Thank you.
Yeah, yeah. So,
Okay.
okay, if
See.
you have no other question or anything else, uh,
Okay.
do you have anything more to say or
No, 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 no.
okay,
It's okay.
okay, okay.
Okay.
So then
Thank you.
we can meet again next time. So,
Okay. Thank you.
bye. See you.
Bye. See you.